How's it going, ladies and gentlemen? Mr. Donnie here again, looking at 16.11 stuff, loose acids and bases. So our objectives are as follows. Classify compounds as loose acids or bases based on how they react. Predict whether X or Y would be a stronger Lewis acid or base based on its chemistry. So that's what we're trying to do. A little review. Remember, the Arrhenius definition of acids base has to do with H plus and OH minus. The Bronsted-Lowry definition has to do with proton donor and proton acceptor. And the Lewis definition is going to be a little different. We're looking at electrons here. So an electron pair acceptor is the acid, and the electron pair donor is the base. So if we take a look at this kind of reaction, Arrhenius would be looking for H plus and OH minus combining, which you're not going to see in this reaction here. Bronsted-Lowry would ignore the OH minus and just go, hey, there was a proton, an H plus, that got transferred to another molecule. So we got our acid and we got our base based on that definition. The Lewis definition is going to ignore the protons, ignore the fact that they're protons, because it could be anything, and it's going to look at those unshared pairs of electrons. So it's like, Arrhenius was like, oh, well, look, it's H plus and OH minus combining. Bronsted-Lowry would be like, forget that. Did you see how H plus is doing that with other things, not just OH minus? And then Lewis came along and was like, hey, you guys are missing the big picture. There are other things besides H plus that are doing the same thing. It's the electrons behind it all. And those are their voices in my head. Anyway, so Lewis is looking at the fact that, hey, it doesn't have to be H plus that's being attracted to the lone pair of electrons. It could be other things. And what this does is it helps us generalize our definition. We can look at other chemical reactions as if they're acid-base reactions. So Arrhenius and Bronsted-Lowry are most useful when we're looking at aqueous solutions, which is what we pretty much have been doing mostly. But the Lewis definition will allow us to look at other chemical reactions as acid-base reactions. They also tend to have incomplete octets, which is why they'll accept an electron pair. If you take a look at this, BH3, it doesn't have 8 valence electrons, it only has 6, right? Because there's 2 in each bond with the hydrogen, and it has an incomplete octet, which is why it can accept the electrons that nitrogen has that it's not sharing. All right, examples. You can have ferrocyanide complex, butchered that. Anyway, you have this iron ion, and you have these cyanide ions, which all have a -1 charge that isn't there. But basically what's going to happen is, all right, carbon's got these unshared pairs of electrons. They're negatively charged. I have this iron ion that has a positive charge. Opposite charges attract. So that's what's going to happen. Iron's going to end up being surrounded by these unshared electrons, making a complex. Okay? So overall, this complex, I think, has a -3 charge, because each one of these are -1, and we got a +3 in there, so overall it's a -3, and it forms this complex. Other examples, did you know that if you put CO2 and you react it with water, you get carbonic acid, which is going to be, I can't do the math. Anyway, I think it's H2CO3. There you go. The way that happens is from a Lewis acid-base reaction. So this oxygen has these unshared pairs of electrons, which are going to be attracted to the carbon, and it's going to make a bond with them. So now the way that happens is one of the carbon bonds disappears, and those electrons get bumped out to the oxygen. So what's kind of happening is these electrons are getting kicked out and no longer being shared with the carbon, and they're just on oxygen. So now this oxygen has a -1 charge, and we got a bond right here. Now what happens is hydrogen is attracted to those electrons that are right there. They're pretty close to it. They're going to be attracted to it. So what happens is that hydrogen is going to get transferred to that oxygen, and it's going to make a bond with it. So now I'm going to redo this, and I'm rotating this molecule counterclockwise a little bit to look like this. So now we have carbonic acid, and this hydrogen can get kicked off and give me H plus ions, which is going to decrease the pH, make it more acidic. So carbon dioxide can affect the pH of water that way. All right, we have hydrolysis of metal ions. Remember, hydro means water, lysis means breaking apart. So we have water being broken apart by metal ions. So metal ions have a tendency to act as acids in solution. And the reason for this is when they become hydrated, they get surrounded by the water molecules. Their positive charge is attracted to the unshared pair of electrons on the water molecules, and hydration is going to cause more polarization of that HO bond in water, weakening it. So I got a good animation for you. So here I have a metal ion. So cation is going to be attracted to the electrons in the water. So I got water. These unshared pairs of electrons are going to be drawn to that positive charge. Right, so I'm going to get something that looks like this. The attraction polarizes the OH bond. So like this iron is positively charged. It's going to be pulling electrons towards it from all of the oxygens, right? Which is going to polarize each of these oxygen-hydrogen bonds, which will weaken it. So now H plus is more likely to get kicked off, and that's what's going to happen. Hydrogen will get kicked off, give you H plus in solution. The pH is going to go down and become more acidic because of that. All right, so metal ions acting as acids and their strength. The higher the charge is on that ion, the stronger the acid is going to be. The smaller it is, so decreasing ion radius, the stronger the acid's going to be. All right, so if we take a look at Cu plus 2 versus Fe plus 3, Cu2 is going to be a little bigger than Fe plus 3. We also have a plus 2 charge versus a plus 3 charge. Well, the stronger the charge, the more pull it's going to have on those electrons, which is going to polarize those bonds between oxygen and hydrogen even more. So Cu only being plus 2 isn't going to do that as much as the iron will. So we got bigger and less charge versus smaller and greater charge. And if we look at the Kas, you see that Cu plus 2 has a Ka of 1 times 10 to the minus 8, whereas iron has 2 times 10 to the minus 3. So it's a huge difference in their acidities. And that's Lewis acids, right? A little summary right there. Lewis acids have to do with an electron pair acceptor, and the bases electron pair donor. So here, NH3 is the base because it is donating the lone pair of electrons, and BH3, which is going to accept them, is the acid. Hope you found that helpful. See you in class. Goodbye.